Right. Now, yesterday I spoke about regression analysis and correlation. And as we've gone along, people have asked me, but can you use different analyses in the same trial and that sort of thing? Now, and we've spoken about disease progress curves as well. So I've got a scenario here where I'm going to mix, I don't know how many, you can count them as I go along, analyses. Okay. I needed to evaluate 10 cultivars for, in a maturity group 6. Now the reason I specify that is I just want to not bring in the issue of different maturity groups and season lengths and physiology and so forth. So let's assume all things equal just for this exercise. Okay, and I need to evaluate them for resistance to soybean rust. So I planted my 10 cultivars in a randomized block design with 3 replicates and got the trial going. The problem is that the trial was far away from my location, and I could only get there every 10 days. And I needed to measure disease onset, or get an estimate of disease onset, and I needed to get an idea of the rate of disease development, and Zach has referred to the area under disease progress curve on a number of occasions as a measure of total disease. Now, if I only, that's just to give you an idea what soybean rust can do if you don't spray your soybeans. It's almost worse than UG99. Okay, right. So what I did is, you'll see I've got a column here, disease proportion. The model I use to quantify my disease progress curve, or to draw my disease progress curve, is the logistic model, and that's the model there. And it works on disease proportion and not disease percentage. So in other words, although I'm using proportion, you can multiply by 100 and you've got the percentage value. Right, so I went through, and 60 days after planting, I got to my trial site, and in that block I measured 0.16, or 16% disease, and in this block it was only 2% disease. Let me just switch Metson Chisi off. Okay, he's no longer online. Right. Then I got there 10 days later. Okay, and the disease had increased to 29% there, or proportion of 0.29. At 80 days it was 0.42, and there it was only 8%, there it was 14%. And so I went every 10 days, okay, and I managed to get a few data points. Now if you look at the logistic equation, it works on basically a linear model that has been log transformed using the transformation x divided by 1 minus x. So you're using the log of x divided by 1 minus x, and you can then take that linear transformation, put it in this equation, and it will draw a disease progress curve for you. Right, so here we have the original data. Those are my 5 data points for each of my lines or varieties or cultivars, whatever I was measuring. Okay. I do the log transformation on that data, and I can, using Excel, fit straight line, simple linear regressions. That value there, we call it the apparent infection rate, can be used then to compare the rates of development of the different, or disease in the different lines. Okay. So I would do this for each replication of my trial. So I had, how many lines were there? 10, I think. 3 reps, so I'd have to do 30 of these regressions to work out the regression formula and the rate of disease development. Once I've got that, I can go back to my table and put it into Excel here, and you'll see I've got that little formula there, and I've replaced those parameters there with my regression parameters on that side and on this side. And now it's simply a case of copy, paste all the way down to the bottom, right, and copy and paste all the way down to the bottom. Okay, and if I go back to the graph I have down here now, you can see my disease progress curves in those two varieties that I measured. Now once I've got that, I can start making deductions about the behavior of those lines or the response of those lines to soybean rust. I can then work out the time of disease onset, and I normally use 5%, just as an arbitrary value. I can either do that by integration, or I can just simply do it by iteration, where I go down my list here, and where's 5%? Try again. 5% is at 46 days. Okay? And in this variety here, 5% was at 68 days. So I can now work out that that value there was 46, and that was what? 80? 68, whatever the case may be. Okay, and I can go to my data table, and from those graphs, I can fill in the rate for each rep. I can fill in the onset date, and if I go back, I can go down to the bottom here somewhere, and I can see that this one reached 100% after, try again. It reached 100% after 148 days, and that one, if you work it out, actually it was about 171 days, but okay, I didn't take it right the way down to the bottom. So in other words, it tells me when the plant basically came to the end of its lifespan due to disease. So the one expired after 148 days, and the other one was at about 171 days. Okay, and I can then put all that data in my table, and I can take it to one of my statistical programs, and I can make all kinds of deductions about what was going on in the epidemic and how the cultivars responded to the epidemic. So cut and paste, and I did also measure yield. You can see that in the, so I can copy that. Now I'm going to take it to a very simple little program that we use. This is NCSS. Very useful for smaller data sets and that sort of thing. And I can just go and say paste, and there's my spreadsheet. I just want to take these out and put them in the variable information. Okay, and I'll just delete that for convenience sake. Right, so there's my spreadsheet with all the data that I worked out from my regression model right there. And I can then do an analysis of variance, use a general linear model, and I'm going to, sorry, let me just try again here. The response variable I'm going to use is going to be onset to start with, and I'm going to use cultivar number and rep because it was a randomized block design. So it's just basically up to one way analysis of variance. And as simple as that, I have my analysis of variance. So there's cultivar number, and you can see that my cultivar effects are highly significant. The rep was not significant, and I can do that for each one of my variables and work out whether there are cultivar differences in terms of onset, the rate of disease development, in terms of the area under disease progress curve, and in terms of yield. And I did that before I started for the sake of speed. And I have all the analyses of variance here. So there's my onset, rate, area under disease progress curve was significant, yield was significant. Okay. And I can then work out the LSDs. If you remember, I did say LSD is equal to square root of mean square error divided by the number of reps times the t value for the degrees of freedom in the error, and you have an LSD value. And you can then work out the significant differences between your different, or the means of the different lines that you're using. Okay, so there was the lowest one, there was the highest one. You can see that they're significantly different. That was significantly different, and I did that for each one of these. And you can then go and look at the table and draw conclusions about onset in the different lines or cultivars or germplasm that you're evaluating, just like you would in any other analysis of variance that we spoke about earlier. So that is very simple. You can look at the yield differences here. There's a low yield, and it goes up to, there's a higher yield there. It goes up to that. And you can see the significant differences in how the genotypes differ from one another.